Alright, are we ready to rock? Let's do a little bit of Algebra 1 review before we get into the Pythagorean theorem. Alright, the distance between A and B is 13. If the coordinates of A are 2, -7, and the coordinates of B are 7y, find y. We've done a few of these types of problems. Similar setup, except this time we know the distance rather than maybe like 2 points are equidistant to the origin. There's always different situations. So, we know the distance is 13. And my distance formula will be the difference between my x's. So let's go with 7 minus 2 squared plus the difference of my y's squared. So y minus -7 squared. Okay. So I got to do a little bit of algebra. So 13 equals, why don't I go ahead and simplify on the inside best I can. So this would be what? 5 squared is 25. Plus y plus 7 squared. Okay, so the square root on the outside is kind of messing with me right now, and as we know from previous video, you can't like cancel out the squareds and square roots because of that addition that's on the inside of the radical. So what I'm going to do is I'm going to go ahead and square. I want to do that in a different color. I'm going to square both sides to cancel out that square root. So 13 squared is 169 equals 25 plus y plus 7. Jenny is currently whining to go outside, aren't you, Jenny? Yeah? I just brought you in from the cold, and now you're wanting to go back out? Okay. Alrighty, so I'm going to subtract 25 to the other side. So minus 25. So I get what? 144. And then that's y plus 7. And there are a few ways of doing this. Some people will FOIL out on the right-hand side. But you know what I noticed just now? I can square root both of these. And it's going to be nice. So I get 12 equals, and that's actually plus or minus 12, equals y plus 7. All right? So I get basically two little equations that I can that I'm going to mess with here. All right. So let's see. I've got, when we do this in a different color, y plus 7 equals 12, and y plus 7 equals -12. Alrighty, I'm gonna scooch some of this stuff up. There we go. And I'm gonna get y equals 5 and y equals -19. Alright, so there we go. We got two different solutions. That is common with these types of problems to have two different solutions. Keep in mind, you could have done things a little bit different. Whoa, holy cow! What the heck just happened there? There we go. You could have squared it right off the top rather than and when I'm referring to these two steps here. You could have just squared both of them right off the bat and done the 25 on the inside all in one step. But I'm trying to show a few steps with these types of problems. All right, let's keep moving here through the bell work. So let's go with number 2. We've got to rationalize my denominator. So what I'm going to do is I'm going to multiply by root 6 over root 6. And I'm going to get 4 root 6 over 6. And if I simplify that, that's going to be 2 root 6 over 3. Boom. Done. Not a bad one right there, right? Okay, so that's apparently shrinking the other one as well. That's not what I planned. All right. Let's go with the next one here. We've got, and I'll make a little space. How about, so root 20 plus root 125. All right, so 20 breaks down to 4 and 5, so that's 2 root 5 because the square root of 4 is 2. And over here, that can break down to 25 and 5, so that's plus 5 because the square root of 25 is 5, root 5. So all this adds up to 7 root 5. Jenny, you'll go outside soon enough. All right, looks like we had one missing there. All right, this last one that did not show up is root 36 plus 64. Okay. Now this is really actually a pretty simple one here, but I wanted to show some of the pitfalls that people have, the mistakes they make. So some people will think, oh, square root of 36 is 6, and the square root of 64 is 8, so I get 14. Heck no. No. All right, let's try that again. Square root of 36 plus 64, I got to add those together first, which is 100, and the square root of 100 is 10. There's my correct answer. All right, and that is another thing that I want to illustrate, much like I was referencing up here. I can't just, cancel out the squares with the square root on that right-hand side and call it a day. It won't work out correctly. That's essentially what we did in this first one, which was incorrect. You can't just square root just because they're perfect squares. Okay, you got to add them together first, and then you can square root. Order of operations. America. Alrighty, we got our Pythagorean theorem families of right triangles. We've done the Pythagorean theorem, but now we're getting to those Pythagorean triples, as they're often referred to, or families of right triangles. All right. Alrighty, the most common Pythagorean families, and yes, you will see some awkward family photos here staggered throughout the video today. So we got our 3, 4, 5, 5, 12, 13, 8, 15, 17, and 7, 24, 25. The most common one that we'll see, or that's used a lot in real life, is this 3, 4, 5 triangle right up here. One thing that people will often do is if they are building something and they want a right angle, they will measure, say, 3 feet in one direction, 4 feet in another direction, then check and see if that is 5 feet. So they would want 3, then 4, then 5, or really any multiple of that. It could be a 6, 8, 10. I can multiply it by 2, by 3. I can divide it, everything consistently. So these can be altered, if you will, all right, by a common factor. Okie doke. Yeah, there's many more of these, but these are the common ones. And if you memorize these 4, then you are Gucci. Okay? It'll help you go a little bit quicker through problems. Alrighty, so we got another wonderful family photo here. That's the crew from It's Always Sunny in Philadelphia. So we've got 4 sevenths, 3 sevenths. What do we think x is going to be? Well, as I said in the previous slide, you can always change these triples by a common factor. In this case, that common factor is 1/7, dividing by a 7th. So we'd have 5 sevenths. Excellent. And you could do Pythagorean theorem to show this. 3 sevenths squared plus 4 sevenths squared is equal to what squared? And you would find 5 sevenths. Alright, we're going to solve this problem here based on what we know about triples. Yes, again, you could use Pythagorean theorem, but with a little bit of practice, these triples, which you'll see quite frequently, will save you a lot of time, and we know that time is money. Okie doke. So what do we have here? We got 10 and 26. That seems to be double of 2 numbers. Jenny, I just let you back in because you wanted to come inside, and now you want to go back outside? This dog here can't make up her mind. All right. So this is actually 5 times 2. This is 13 times 2. So this needs to be 12 times 2, which is 24. Boom! It's a 5, 12. 12, 13 triangle times 2. Everything been double. Alright, so we've got to find some missing sides once again based on what we know about triples. And we have a lovely family photo of a family that looks like they just took a trip to Hawaii. And we're maybe putting together a nice holiday greeting card for friends and family. Alright, so at first glance, this one might appear to just be a 3, 4, 5 triangle, making this 2.3 if you were to, add 2 to everything. However, you can't just add the same thing to everybody. Okay? You can't just add. What you have to do is it has to be a common multiple. If you were to put this into the Pythagorean theorem, this would not work. Okay? If you did 2.3 squared plus 2.4 squared, it would not equal 2.5 squared. This is actually a 7, 24, 25 triangle divided by 10. Okay? So if I were to move that decimal place on each one, Boom, it is 0.7. Cool. So you got to be careful. All right. So once again, same type of thing, but with different numbers. All right, 16 and 34. Well, since I know my triples so well, I noticed that this is the same as, let's see here, 8 times 2. This is the same as 17 times 2. So this must be 15 times 2, which is 30. It's an 8, 15, 17 triangle. Now, I know a lot of you are probably thinking, why don't I just set up the Pythagorean theorem and solve? You can do that. That is fine, but this will save you time. All right, and these will also come back in Algebra 2 honors as well as a lot in pre-calc honors. Okay, so these will continue to come back, and it's a huge time saver to not have to do Pythagorean theorem. Alrighty, a little bit of application. Let's see here. Find the diagonal of a rectangle whose dimensions are 9 by 12. Okay, so if I draw a rectangle, 9, 12, I want to find the diagonal of it. 9 and 12. Now, what is that? Ooh. Once again, since I am super proficient in my triples, I notice that this is the same as 3 times 3, 4 times 3. So what's 5 times 3? It is 15. It is a 3, 4, 5 triangle that's been tripled. A triple. Woo! All right, so you got to be careful on these bad boys. All right, we got danger, thin ice. That's right. The river just froze up, so I have a feeling it's rather thin ice as well. I have not seen any snowmobilers yet. All right, so I've got 3, 4, must be 5, right? Well, that's where you just be dead wrong. No way. The hypotenuse has got to be the biggest side, right? So you do have to be careful. I would have to Pythagorean theorem this bad boy out. X squared equals 4 squared. So I get 9, 16. Ooh. Jenny's outside, and I think she just saw a dog walk by or something like that. All right, so I've got to move this around because I'm running out of room. Okay. So x is equal to, well, 16 minus 9, oops, that's x squared. 7, square root it, so x is equal to square root of 7. So do have to be careful about jumping the gun in your triples here. But again, they are a huge time saver when used properly. All right, we got another problem here, solving for x. Well, looks like it's going to be a couple parts here to get to my spot that I want. Well, 12 and 9, we just saw that recently, right? That's a 3, 4, 5 triangle that's been tripled, which makes this guy 15. Ooh, there we go. And then that's an 8, 15, 17 triangle. Boom, done. You see how quick that was? If I had to use Pythagorean theorem, I'd still be writing it out. All right, but with the triples, being comfortable with the triples, saves a lot of time. And time is money. That ain't funny. Whoop, whoop. All right, we got ourselves a little word problem here with Miss Jenkins leaving Huntley High School and heading to GameWorks. All right, so Miss Jenkins leaves Huntley High School at 5 a.m. for a morning jog. I believe it's pronounced with a soft J like that, yes. And she travels east at 6 miles an hour. So let's say we got whiny Jenny over here wanting to go back outside even though I just brought her back in. So this is Huntley High School right here. There's little Jenny there. She's whining a lot today, wanting to get back outside. But it's just too cold to stay outside for too long, so she's got to take little breaks, and she's not happy about that. All right, back to the problem. So she travels east at 6 miles an hour. There we kind of go. All right. And that's at 5 a.m. And then at 7 a.m., she turns south. So if she traveled from 5 a.m. to 7 a.m., that's 2 hours at 6 miles an hour. That's 12 miles. Right? Okay. And then at 7 a.m., she turns south and travels 8 miles an hour. And at 9 a.m., she arrives at her destination. So for another 2 hours, she's running at 8 miles an hour. This is impressive stuff. So that would be 16 for this guy here, if my marker would write properly. 16 miles. And I got that by doing your, let's see here, whoop, doing 8 miles an hour for 2 hours. Boom, multiply them together. All right, so how far is Huntley High School from GameWorks? And we're talking about the diagonal right here. Geographically, how far is it? Yeah, you got to take roads and things like that, but if you went straight shot, how far is it? Well, that's a 12 and a 16. If I remember correctly, that's basically, that's a 3, 4, 5 triangle that's been multiplied by quattro. All right, because this is 3 times 4. This is 4 times 4. So 5 times 4 is 20. 5 times 4. So she's 20 miles from HHS. Yeah, yeah. Woo, woo.